to about 1,000 megaparsecs, or maybe a little bit less, this is an actual picture of galaxies, the little bit older one. Now you get even better pictures. We see that essentially it's at about 1,000 megaparsecs. The universe is like a simple fluid. It's like water almost. It's every point in that fluid is one galaxy. It's smooth, it's homogeneous and isotropic, as we'll talk about it a little bit later. And every point almost is the same. So one way of looking at it is that as we look up, as we go from the planetary to, let's say, this cosmological, astrophysical, then the cosmological scales, the universe looks simpler. And the other way of looking at it, that as we look up, we seem to realize that we are less and less special, right? So we are just one of the 8 or so planets in the solar system. Our sun is one in many, many millions in the galaxy. Our galaxy is 1 in a billion, right? And then finally, we are here in this kind of scenario where we are just a speck of dust, right? So in fact, our universe at large scale in a certain frame, it looks completely homogeneous. It means it looks the same everywhere. So no place in the universe is preferred. It's all the same everywhere. And it's also isotropic. It means no direction in this spaces in the universe is special. So in a way, we are not special as well. It's easier to say it now, for we know that some of the people who said it historically in the past, one of them lost his life, the other liberty, just basically trying to say that we are not special. So it's easier said than done. In any case, from the physics point of view, we come to the so-called cosmological principle, which, exactly as I said, is, and also as observed, to a very high degree of accuracy, that our universe is completely homogeneous, is the same everywhere, and isotropic, which is the same in every direction. And then you have to do a little bit of mathematics. So you can, for those of you know, great. For those of you who don't, it's pretty straightforward mathematics. But for now, you can accept it from the following statement, which is that it's a mathematical fact that if three-dimensional space, we live in a three-dimensional space, right? If three-dimensional space is observed to be, or assumed to be, we assume because we observe, to be homogeneous and isotropic, that is the same everywhere and the same in all directions, then there are only 3 possible three-dimensional shapes. So remember, it's three-dimensional. It's not like a two-dimensional sheet. It's a three-dimensional object. So it's a little bit tricky to visualize. But in any case, there are only 3 distinct possibilities, 3 and only 3, no more, no less. The first is that space is completely flat. That's zero spatial curvature. The second is it's a sphere, so it's like a football, okay, but three-dimensional though, so it's hard to kind of visualize. So it's like a three-dimensional football, okay, three-dimensional sphere. Or it's saddle-shaped. It's like a saddle, which has negative spatial curvature. So if I depict it, right, I'm trying to move my control so that I can see the screen. Anyway, so if I can depict it mathematically, so I've drawn 3 two-dimensional pictures because I cannot draw 3-dimensional solid pictures on a 2-dimensional whiteboard, right? So this is like a sheet of paper which is completely zero curvature. It is zero curvature, so the Gaussian curvature, some kind of measure of curvature, is 0. A sphere which has a positive curvature, and a saddle which has a negative curvature. And these are the only 3 shapes that's possible. Now, the distance between 2 points, we know that in the case of Cartesian, flat space, the distance between 2 points in, let's say, 2-dimensional polar coordinates or spherical polar coordinates is given by this expression. So between 2 points separated, by dr and d theta or d phi, is dr squared plus r squared d omega squared, the angular part being d omega squared. For the sphere, it's a little bit different. It's almost this, except the dr squared term gets a little bit modified by this, something like this here. And for a saddle, it gets modified, but with the opposite sign. So you can see clearly from here that if you have 2 points, like on a flat space, then if you make it into a sphere, the distance between the 2 points, like the geodesics, like the a great circle, the distance increases because it's 1 minus. And then if it's a saddle, the distance actually decreases, right? So this fully characterizes any of the three spaces. And just to emphasize, since our universe is observed to be homogeneous and isotropic, it must be one of these three shapes. Just extrapolate in your mind to one extra dimension, but essentially it must be this, okay? So succinctly, it can be, these three can be summarized by this so-called metric with k equals 0 plus or minus 1, where k equals 0 is the flat space, 1 is the sphere, and minus 1 is the saddle. Now, our space-time is four-dimensional. Our universe is four-dimensional. And so far, I only talked about space. So we have to somehow import the time, because the actual metric, the space-time metric, so distance between two events in the universe, is a space-time object. It's not just space. So you have to add the time, right? Now, the only way that you can add the time, well, is some kind of dt squared. But the only way to add the time and make this distance between the 2 points in space-time preserving homogeneity and isotropy, and think about it, and like try to convince yourself that this is indeed the case, is when you have this spatial part of the metric, you have a time part, and only a factor, which is known as the scale factor or the length scale in the universe, multiplies this. So this cannot be a function of space, because if it's a function of space, it will break homogeneity and isotropy. It can be a constant, of course, but it doesn't have to be a constant. It can be a function of time as well. And indeed, our universe is a dynamical, it's evolving universe. So all the evolution of the universe is contained in this one scale factor here, right? So this is still I have not put in any dynamics except saying that A of t is dynamical, right? Can be dynamical, can be changing in time. But whenever you have a quantity which is dynamical, which can change with time, you have to say how it changes with time, right? And the way we define how something changes with time is we define or we specify the differential equation that it follows, right? All equations, fundamental equations in physics, are differential equations. Why? Because differential equations have derivatives in them. Derivatives are slope. If you know the slope, you know the rate of change, so you know the change. If you know the change, you can predict. You can predict the future, or you can predict in space, like away from where you start, right? So therefore, you have to give the differential equation which governs this scale factor. And at large distances, at cosmological distances, the only force which really matters, as you can probably guess, the only force that's relevant is the force of gravity. And what are the differential equations which govern the force of gravity? Now, there are two sets, if you like. One is the Newtonian laws of gravity, and the other is Einsteinian or the general relativistic. Of course, they're not independent in the sense like you can derive the Newtonian set in low energies from Einstein gravity. And I'll speak about Einstein gravity in just a second, like general relativity. You could ask that if general relativity does all the job, it is the correct theory, why even bother to talk about Newtonian gravity? Well, the reason is that Newtonian gravity, although it's not the perfect theory, neither is Einstein, presumably, but Einstein's theory, general relativity, is a much more precise theory which incorporates Newtonian gravity. The reason I mention Newtonian gravity is that even though it's not perfect, it works very well. In fact, most of the cosmological analysis, or most of it, a lot of it, not all of it, of course, a lot of the cosmological basic conclusions can be even drawn from Newtonian gravity. But anyway, since we're talking about space-time, metric, and all that kind of thing, it's best to go to Einstein gravity. So the evolution of the dynamics is given by Einstein equation. If you know it, great. If not, it's a set of differential equations, since it's gravity is a nonlinear theory like Yang-Mills theories. So it's not the only one, but the first one. The equations are could be considered to be quite nonlinear and horribly nonlinear, difficult to solve, but they're differential equations, some indices, right? And since it's assumed that, if you remember that picture at 300 megaparsecs and so on, that if it's it's very smooth, homogeneous, isotropic, almost like a fluid, it is legitimate to assume that that scales the matter part of the universe, or matter density, or matter energy, if you like. So anything which is matter and energy in the universe can be suitably modeled by a perfect fluid. A perfect fluid is one in which its pressure and densities are related by a simple constant W. Okay, so it's a perfect fluid. And I've put C equals 1 somewhere, right? But so you assume. So why do you need to assume that? Because as many of you would probably, many of you would probably know that Einstein equation, which is this. So never mind the details if you are not too familiar with it. On the left-hand side, you have some terms which has to do with space-time curvature. So it's geometry. It's geometry on the left-hand side. On the right-hand side, T mu nu are so-called stress energy tensors. So as you can see, they're matrices, but essentially they're the components of the entries of the matrix is density and pressure. So it's matter, right? It's matter or energy, and E equals mc squared. So matter and energy can be interchangeable. So Einstein's theory, the very interesting thing is that it connects geometry with matter. So when you have matter, it influences geometry. When geometry is different from flat, then that says that there is some matter or energy somewhere. Okay, so that's the basic idea. So once you put in the matter and energy at those scales in the universe, which as I said is assumed to be a perfect fluid, sorry about that again, you put it in, and remember that the only dynamical quantity that's there in the space-time, let me remind you, is the scale factor. That's the only thing which is a function of time. There's nothing else that's there that's dynamical, right? So therefore, it's no wonder, oops, sorry, about that. I should find a better way of changing the slides. Maybe I should do it this way. Anyway, so no wonder that if you put that metric in the Einstein equation along with the perfect fluid, what you end up with is a set of two independent differential equations, one for the velocity and one for the acceleration. Okay, so A dot is dtt of A, the scale factor. It's essentially the velocity, and double dot is d2A dt2. So it's the second derivative of the scale factor, so acceleration. So roughly speaking, A dot gives the velocity of the universe, or velocity of expansion, or velocity of expansion, because we see it expanding. It could be expansion or contraction, but anyway, in reality, it's expansion. And A double dot, the acceleration, and they're both, as you can see here, they're both functions of, or they both depend, the velocity and acceleration, they both depend on the density and pressure, as it should be. That's the properties of the perfect fluid. Before I go to the next slide, let me define a few quantities which I would use for the future slides. One is the so-called redshift. The redshift is essentially, it's defined to be the scale factor that we have now. A0 is a reference, -1. So this, so if the universe, you can choose A0 to be 1, right? So if the universe is not expanding, then A is always equal to 1 and the redshift is 0. If the universe is expanding, redshift is positive and vice versa. And this redshift is precisely the Doppler shift factor that multiplies wavelengths. So if you look at a spectrum of some element in a distant star, in a distant galaxy, since they're all receding away from us, they're all redshifted. It's like a Doppler shift just like a Doppler shift of sound. When you hear a train whistle, the train is approaching or going away from us, the frequency changes. The same thing happens here, and it's conveniently given by there's redshift factor Z, which is a dimensionless quantity. And so all frequencies, all wavelengths and frequencies as well, but all wavelengths of light from any source, they are stretched by this factor. So the more the universe expands, the more stretched it will be. Velocity, as I said, is defined to be this way, and you can suitably define it by defining quantity A dot over A, which is the logarithmic derivative of the scale factor. So it doesn't care about the absolute scale A naught. You can write this as proportional to the so-called Hubble parameter, where the Hubble parameter is A dot over A. So it's the logarithmic rate of expansion of the universe. If the universe is not expanding, the Hubble parameter is 0. Right? It was thought previously it was called Hubble constant, then one realized it doesn't have to be a constant. The horizon is the inverse of the Hubble. This is kind of the distance on until which signals have been reaching us until now. So it's the horizons. You can't really see beyond. It's not a fixed horizon in the sense like my horizon is there. If you are far away, your horizon is somewhere, different here. But the distance from myself to my horizon and the distance from you to your horizon, that distance is roughly the same, which is 1 over the Hubble parameters. Sorry. I have to do something about this. Okay. And as I said, if you have an expanding universe, as is the case, Z is positive, all Doppler shifts are towards the red, and Hubble is positive. For a contracting universe, which we don't see, but it could have happened, it could happen later, a few billion years down the line, who knows? Red shift is negative, so it's really a blue shift. So I've drawn it in blue. And the Hubble parameter is negative as well. Now, the first 3 lines on the top of this slide is essentially, the first line is the Einstein equation, one of them. The second line is a solution of the Einstein equation where you see how the scale factor actually evolves. And you can see it's some positive power of t, right? T being the time, which means that the scale factor increases with time monotonically, which means that our universe is expanding. You can take the second derivative and find what the acceleration is. You should do it. It's an interesting exercise. And the third line is how the density of the perfect fluid dilutes as the scale factor increases, or with time. Either way, you can substitute for A here, time, and you can find how it evolves in time as well. And the last, like the fourth line, is the Hubble parameter, which we see first is not a constant, it's a function of time. And in general, except for a very special case when W equals -1, it decreases with time. So it kind of becomes more and more steady. Now, about perfect fluids, we assume from experience, from theoretical considerations, but mostly from observations, right, is that our universe mainly has 3 components in the perfect fluid. The 3 components, the first part is relativistic matter or radiation, photons, cosmic microwave background, neutrinos. And for that, you can show that W is 1/3. So pressure, so 1/3 is like something order of 1. So pressure and density they're both non-zero, both of the same order of magnitude, because relativistic is moving very fast, right? So it exerts a lot of pressure. So it's equal to the density. Non-relativistic is very cold. It's like nothing is moving. V is almost equal to 0. So pressure is 0, right? So it's like you take a gas and like freeze it to like a few degree Kelvin or something like that. So this doesn't exert any pressure. So that's non-relativistic. This is mostly the constituent of what we observe in the universe, visible matter as well as dark matter. I'll make a case for dark matter. But before that, if we just assume that there's a lot of visible matter, we like the light and everything, that image light that we see, and dark matter, they're both non-relativistic with W equals 0. And there's a third component, which is known as the cosmological constant. Sometimes a variation of that is referred to as dark energy, to be precise. I'm just being a little bit loose here, like casually referring to dark energy. There's some subtle differences, but anyway, at this point, it's not this important. So there's a cosmological constant for which W equals -1, right? So therefore, cosmological constant exerts negative pressure. And if you put these things in values of W and so on in the Einstein equation here, it's very easy to show that depending on what kind of matter you have different evolutions of the scale factor. And if radiation dominates, you have like this. If cold matter dominates, you get this T power 1/3. And if the cosmological matter dominates, then you see it's interesting. You have this exponential. And you can clearly see that because of the power here is like less than 1, and then exponential. In the first 2 cases, the acceleration will be negative. So it will be expanding universe, but slowing down. And the last case is not the case. In fact, it's a runaway solution. It expands faster and faster exponentially, right? And it's not a wonder because the cosmological constant exerts negative pressure. Negative pressure is like, loosely speaking, it's like anti-gravity. It's like anti-gravity, right? So therefore, if there's only gravity, normal gravity, then the universe may have exploded at Big Bang or whatever. So it's expanding, but it's eventually going to, so it's expanding, but it's eventually going to slow down, right? But if it's a cosmological constant dominated universe, so it depends on which one's dominating, right? If the cosmological constant is dominating, then it's going to like explode faster and faster, right? So it's not going to slow down at all. So you can see clearly, and the third, well, first column, second column, third column, fourth column, it's how the omegas are essentially the densities as a ratio of something called the critical density. So basically, you make the densities dimensionless. Essentially, they're the rows with, make them dimensionless. And as you can clearly see from here, that the radiation, like just from the powers of the scale factor, the radiation of the relativistic forms of matter, right, like CMBR or like cosmic microwave background radiation and neutrinos, they would dominate in the early universe, very early universe when it was hot. The non-relativistic matter would dominate in the intermediate regions when it's cold. However, you can never beat an exponential, right? Exponential is like the power of compound interest, something like that. So even if there's a little bit of cosmological constant at any epoch, right, eventually it's going to take over. Eventually it's going to take over. So I said late, when it's very cold, and it's going to dominate, and the universe, even if there's a little bit of cosmological constant ever, it's eventually going to dominate and make the universe accelerate. So I will ask, since it's about half an hour, like, are there any questions? Should I stop for questions, or should I just continue?
If anyone in the audience has any doubts, please feel free to come up and talk to the professor.
I know infinite number of things you didn't understand, none of it. So you ask, otherwise why you come? Jai? हमको तो लग रहा है ऑनलाइन सभी
Sir, we do have a question.
बैठ के अपना अपना क्वेश्चन लिखेगा. आपको हम बता रहे थे, आप लोग सुने नहीं थे. चैट बॉक्स से सब लोग क्वेश्चन भेजेगा, so that he will fill one by one. And
Good evening, sir. Good morning, I guess that it is evening here. So, my question was, you said that the Hubble constant isn't really a constant. So, can you elaborate a little bit on that part?
Right. So, okay, a very good question. I'm glad. So please ask questions. So thank you for your question. So Hubble constant, yes. So Hubble. So you can look at it two ways, right? So from the observational point of view, Hubble constant is just defined as the rate of change of the scale factor with the logarithmic dependence. So, okay, from the observational point of view, right? So that's what is defined. So there's no reason why it has to be same at every epoch. It's like everything, right? If you have a car, it doesn't have to go at the same speed all the time. It depends on, its internal dynamics, right? So you can put in the brake, you can put in the accelerator. So there's no reason per se that it has to be constant. And it depends on the observations. If it's observed to be constant, then it's constant, right? But there's no per se or a priori reason why it has to be constant. That's the observational way of saying. From the theoretical perspective, as we clearly see here, it is a function of time or the scale factor, depending on what's the dominant form of matter is. So from the theoretical side also, you see that, in fact, this fourth line that I've written here, this is true only if W is not equal to -1, as you can see here. And here, in this case, it is indeed a function of time. Okay, it's only in the case of the cosmological constant that it is a constant. It is a true constant, right? But and you can prove it from the Einstein equation. So from the observational side, there's no reason why it should be a constant. From the theoretical side, we see that indeed the simplest model, which is Einstein's general relativity, does indeed predict that it is not a constant in most cases. So you can approach it from both sides. Does that answer your question?
Yes, sir.
Okay, thank you. Are there any other questions, quick questions? I can again stop in another 15 minutes or so.
Sir, there are no questions. You can continue, sir.
Okay, thank you. And I have about another 15, 20 minutes, or?
Sure, sir, you can take your time.
Okay, thank you so much. Right. So just to recap, to remind that we have primarily three forms of matter in the universe, but I will talk about the proportions, but so one is very fast, hot, and relativistic matter. One is cold, slow, cold matter, which could be visible or dark, and the cosmological constant. These are certainly possibilities. Now let's come back to the theory once again. It's interesting. So the first equation, right, is the Hubble. So is the Hubble, right. So let me explain the first equation. The first line after it says theory, the first part, A dot over is the definition of Hubble, right? You can change elementary calculus, you can change from A to the scale factor, from the scale factor to the redshift. There's a 1-to-1 mapping, right, between the scale factor and the redshift. So you can change the derivative. And the second part here in terms of Z is the same as Hubble written in terms of the redshift. The second part with the square root, now I have taken, and I will go back to a previous slide for just a second, hopefully not confusing anyone. Here you see in this part here, and maybe I should have written in this way, if you put k equals 0, just for simplicity, okay, you have a dot square over a square, which is h squared, right? H squared, h is the Hubble. On the right, you have density, right? So h squared is the density, okay? And the density has these three components here. Remember, I changed the density from rows to omega. That's just making it dimensionless by dividing it by scale. So essentially the density. So h squared, the Hubble square is the density. The Hubble square is the density. Therefore, the Hubble is the square root of the density with g's and c's and all that kind of thing. No h bar, so it's all very classical. Just want to emphasize. There's g and c. I put c equals 1, but there's no h bar. So the Hubble square, or the Hubble is the square root of density, and now you can have three densities. So you have this three, like this summation from I equals 1 to 3 if you like, and the three densities evolve in three different ways in powers, right? So I put this in here. So here, once you have dt, now you can take the dt to that side, you can dz divided by square root. Essentially you have this dt, just inverting, is looks like this. It's an integral over z, where the first term is the cosmological constant, the second term is cold dark matter or visible matter, the third term is radiation, which is very small, and the fourth term here is the curvature term. If the universe was not flat, you have this, okay? So let's take a quick look at this formula. Now if you integrate it, let's say from 0 to t, on this side you integrate from 0, which is now. So if you look, now is like distance and times are interchangeable, right? Because distance is speed of light times time. So when I say now, I also means like I'm looking right here, right outside, okay? Or just my galaxy, let's say. And when you increase z, you are increasing the distance, you're increasing the time, but by increasing the time, you're also looking back in the past, right? Because when you say something 1,000 million light years away, if I'm observing something, I'm observing something which happened 1,000 million years in the past, right? So if you integrate from 0 to infinity, it's from now until when the universe was really, really small, Big Bang or not, like really, really small, when the redshift was almost infinity, right? If you integrate this, what does this give? From 0 to t, this integral essentially gives the age of the universe, right? So you can estimate theoretically the age of the universe simply by doing this integral, right? And you can do some of it, you can do analytically, numerically, you can always do, oops, I don't know what's happening. It's my computer is gonna not behaving itself. Anyway, so but you have other sources of estimating the age of the universe, right? For example, geological, we know that the Earth, from just geological research, their Earth is at least about 4.55, some kind of that number, billion years old, the sun. So there are other evidence which say that our universe cannot be younger than, let's say, 8 or 9 billion years, because we see objects which are that old, right? So it can be younger than that. So if you put in that constraint, you can actually show that you can put k equals 0, not a big problem. You can put r equals 0, make r equals 0, because you don't see that much radiation now. It's like, it's cold out there. You have these two terms here. You can actually prove quite easily that, that if omega lambda is 0, if you assume a universe without a cosmological constant, the numbers don't work out. The age that you'd get here is going to be quite is much smaller than even the geological estimates of our, of our astrophysical objects' age around us, right? So there must be a cosmological constant. So keep that in mind. I'll kind of suggest an exercise. Do it at your leisure if you have time, if you're interested, which is you can actually derive this equation, most of it anyway, or all of it, just from Newton's law of gravity. And if there are any questions later, you can ask me or whatever. And many textbooks do it as well. And this is dependent on Newton's law of gravity, which is a 1 over r square force, or 1 over r potential, right? You can try to change the law of the force to say from 1 over r squared to, I don't know, 1 over r cubed, or 1 over r, or 1 over r4, or exponential minus r, do whatever you want. And you can see how this Hubble's law changes and how that affects the age of the universe. That's an exercise that's worth doing for any students or researchers. Anyway, so that's the age. We can do something else. We can do a little bit more. Now you can define something called the luminosity distance of any distant astrophysical objects. It's defined as and I'll tell you why it's defined. It's the square root. There's a 4 pi here basically because the area of a sphere is 4 pi r squared. That's where the 4 pi comes from. But anyway, this capital L is the absolute luminosity. It's like you have a 100-watt light bulb, and it's like this 100-watt. It's like the luminosity that you see if you like stare at it from a very close distance. And L is the apparent luminosity that you see from here. And the square root, like the ratio, the square root of the ratio gives a estimate of distance because, well, two things. Firstly, you know, if you have a 100-watt light bulb, you know how it looks like. If you take it far and you see it from here, the luminosity will be less, right? And if you're measuring with a precise, powerful, precise apparatus, from what you see here, you can get a good measure of the distance, okay? And the reason why there's a square root here is because we know that the apparent luminosity will be the absolute luminosity divided by r squared because it's spread out over a sphere of radius 4 pi r squared. So that's why you have this 4 pi and you have d. If you take the square, you get a d squared. Okay, it's essentially that. The only caveat is that what I kind of naively said, like explained to you in simple terms, that picture is strictly speaking, it's true only in flat space, right? If it's not flat space, a lot of things can happen. For example, if you take this 100-watt light bulb there, we keep it there, everything what I said is fine. And then if the universe starts expanding, then in addition to the fact that it's at a distance, you have to take into effect the Doppler shift as well, right? Now, the Doppler shift would depend on how fast, how quickly the universe is expanding. And that depends, as we saw, that the expansion of the universe depends on what matter is in there, right? Because the Hubble's law has all these densities in there. So long story short, if you do the calculation, again, it's half a page of calculation. It's not too difficult at all. If I had 15 more minutes, I could have shown the calculation. Is the luminosity distance, on the one hand, you can measure it observationally, if you know the absolute luminosity of some object. Theoretically, from Hubble's law, which is from Einstein gravity, general relativity, you can derive an expression for the luminosity distance. As you can see here, it's again an integral on that kind of thing. 0 is here and now. Z is the distance of that astrophysical object, okay, star or supernova or whatever. And you have to integrate over this factor. So the luminosity distance, theoretically, as it should, depends on what's the matter intervening it, right? As it should be, because if it's flat, it's one thing. If it's expanding, it's another thing. If it's expanding faster, it's going to be another thing, right? So the Doppler shift has to be taken into account, and the Doppler shift depends on what matter is in there. So it makes perfect sense. Okay. Now, so we have the luminosity distance. Now, the observation, interestingly, if you actually look at the observations, the first observation here, this is the observation which Hubble did, okay? And he measured the velocities of astrophysical objects, right, at different distances. And he actually saw that as you go further and further, there is always the velocities of the astrophysical objects is not constant. It's not a horizontal line. It keeps on increasing. Correspondingly, everything is slowly, more and more redshifted, okay? And this is, again, I forget, I try to give all the references unless it's open source thing. Anyway, so these are, these are measures. These are measures. I don't know what's happening with the computer. These are measures of, I forget, some simple element. I don't want to guess without say something wrong anyway. And as you go on the right, like as you go like down, as you come down, it's further and further. And as you can see, the spectrum is almost identical, except is more and more redshifted, right? And this shows beyond any doubt that our universe is expanding, which is what Hubble found. Here, of course, theoretically, it can be predicted from Einstein's equation. Edwin Hubble here was the first person to actually observe it. Georges Lemaitre was a Belgian priest, and he, following Einstein's theory, he probably believed in that model better than Einstein himself, because he had actually argued that it's quite possible that the universe is expanding. I think even before Edwin Hubble's observation. So it's very interesting. It's a very interesting synergy between theorists and an experimentalist, right? So some predicted and some observed. Now coming back to the luminosity distance, which is what is essentially measured, okay, versus the redshift, which is more and more distant objects. And as I said, I gave the example or the analogy of a 100-watt light bulb, because if you want to judge, if you want to estimate the distance of an object, right? It could be an astrophysical object, it could be a 100-watt light bulb. From what you see here, you must know what is the intrinsic brightness of that object, right? If you don't know what the intrinsic brightness is, you don't know where it is, how far it is, right? So for that, in cosmology and in astrophysics, you use something called standard candles. Standard candles are objects whose intrinsic luminosity is known for whatever reason, right? And one of the standard candles, which are very convenient, is called are type 1a supernovae. And here in this picture, they're about 42, I think. This is one of the earliest pictures. I should probably update it. There are hundreds, thousands actually by now, I believe. And here it's the same. This picture is very similar to Hubble's picture, as you can see here. The only difference, well, there are two differences. One is here for Hubble, the Z on the x-axis was very small. The extent, the range, the domain of Z was like 0.01 or something like that. Whereas here, it's high redshift. So the domain of Z is up to 1, right? So it's high redshift. Why is that important? Because the higher and higher you go, the formula, like, for small values of a variable, everything is linear, right? Any function f of x is linear for small x. I mean, I'm just saying, in most cases anyway. But it's only when you go to larger and larger x, you actually see the real shape of the function, right? Just think of simple Taylor expansion, okay? So you need higher and higher values of the redshift objects so as to get a better and better understanding of what the universe is made up of, because that gives you an estimate of the matter. Now, that's the first difference, that this is high Z. This, well, of course, is a supernova as opposed to stars or clusters. That's also a difference. It's a technical difference, important one. But there's another important difference. As you can see here, if you can see, it's quite clear from here that the best fit curve of these objects is no longer a straight line. Exactly as I said, fx equals x for small x, for any function x, small function. Anyway, so if you look here, in this corner, it's a straight line. But as you go towards higher and higher Z, it deviates from a straight line, and it deviates upwards. Okay, it deviates towards up and not down, right? And that simply means, exactly as it shows, that that the universe, it shows from here that it's not only expanding, there's a positive velocity, the acceleration is positive as well, just from the shape of this curve, okay? And that's why measuring high redshift was so important. And as the shape of the curve is positive, it's accelerating. For one thing, it shows that there must be a cosmological constant, right? There must be a cosmological constant, because that's the one which makes it anti-gravity. That's one which makes it accelerate. I kind of, in half in jest, I put this tree ring picture here. It's like the more rings you see, the more information you have about the weather which was there 100 years ago. So it's something similar. The more redshift, the more supernova that you see, you have more information of what's intervening from now until, say, 1 billion years in the past. So it's just an analogy. And why are type 1a supernovae used? Because they are standard candles. They're exploding white dwarf in a binary system, and its absolute luminosity about 10 power 44 joule. It's hardly a candle, but it's pretty standardized. Almost all supernova come with that energy. So it is like a 100-watt light bulb in the sky. And the light curve is also, you see, it's pretty standard. It's depending on the irrespective of the supernova, of which exact supernova. It's like a standard light bulb there. Supernova were known to exist for hundreds of years. In fact, in many ancient literature, like this one, it's a Chinese text of the, I forget now, 13th century or maybe even earlier, I should look it up, where apparently they have a reference to supernova. And if you can read Mandarin, maybe you can see if that's the case, but that's what I've been told. Anyway, and it releases a huge amount of energy. And long story short, if you again look at this curve here, okay, even if you look at this curve here, the best fit curve, in fact, corresponds to these four quantities. So firstly, we see from that curve, the best fit curve that is, that our universe is flat, spatially flat. It's not, space-time is curved, but spatially flat, it means simply that, it's a flat space, but also basically it means that at any given point of time, the Pythagoras theorem is valid, Euclid's axioms are valid, right? The Pythagoras theorem is not valid on the surface of the Earth, as we know, right? But it is valid in this universe. It needn't have been. It's one of the three possibilities, but somehow it chooses this possibility. Second, the proportionality, the proportional value of the cosmological constant is 0.7, which means about 70% of our universe is the cosmological constant. About 30% of our universe is matter, visible matter, right? And out of this 30%, you can do a more careful study, and you can show actually it's only 5% which is visible. So 25% dark and unknown, and only 5% visible. And radiation is negligible, so you can even set it to 0 if you want. So it's a spatially flat universe, right? It has 70% dark matter. It has 25% dark energy. It has 5% visible energy, very little radiation. It is homogeneous. It is isotropic. It's governed by the laws of general relativity. So this is, how much simpler can it get, right? So it's extremely simple. I would argue that it's governed by simple set of laws, general relativity. It has basically just two kinds of matter/energy, the cosmological constant, which is 70%, visible matter, which is 5%, and dark matter, which is 25%. So that's the good news. But the bad news is the same news, which is 70% dark energy and 25% dark matter. So 95% of our universe, we really don't know what it's made up of, right? So that's the unknown. So it's known and the unknown. So for that, the 2011 Nobel Prize in Physics was awarded to these three scientists. You can clearly see that they're quite happy. Now I go quickly. I'm kind of cognizant. I'm aware of the time, so I'll probably take another 5-7 minutes. Is that okay?
Yes, sir, you can extend the time. It's fine with us.
Okay. But I'll not take a long time. Maybe 5-10 max. I don't want to bore everyone. So, but thank you for your patience. So this is a picture of a brief history of the universe. I wouldn't go too much into it. I just say that basically, again, look at this, like time along the x-axis and the scale factor along the y-axis. The scale factor increases, expands, and then in the late universe, it curves, it bends, and the bend will be exponential, right? So even I don't think I've had any slide, but if you see, if nothing intervenes, exponential, you can't stop an exponential, right? So in a few billion years, like our universe will kind of rip apart, right? Because this means that the distance between galaxies would be exponentially large. So you can't really see our galaxy, like our Milky Way, we can still see, right? But all the other galaxies that we can see with the naked eye or the telescopes, they'll be too far and too dark. So our sky would be pretty dark, and it'll be like accelerating like crazy. Okay, so that's the picture, and it's pretty smooth until then. And if you can see Big Bang, we don't know exactly whether it happened or not, but it was definitely very small. So it could have happened, or it could have been a cyclic universe or something like that. But here you can see here that there's an exponential phase of expansion also at the very, very, very early universe, which is known as inflation. I'll probably not go into the details today, but just a picture. And microwave background radiation, I just wanted to mention, this was one of the first instances that where it was shown that that the radiation surrounding us, all the 4 pi steradians, right, solid angle, it's pretty homogeneous isotropic. So I keep emphasizing that this picture, it's a color-coded picture. So the blue regions are hotter and red regions are colder. So it doesn't look like homogeneous isotropic. So this is the full sky. Okay, so this is that same geographical projection which you do to draw atlases to cover the whole Earth. This is exactly the same sphere, except it's not the sphere from here. It's like it's from the inside, right? So it's the celestial. And although it doesn't look homogeneous here, it is. So the difference between the red, yellow spot and the blue spot, the difference in temperatures between them is about 1 in 100,000, so 1 in 10 power 5. So it's pretty perfect black body. So the question is, why this incredible homogeneity and isotropy? You could ask, why not? Well, the reason is that you can again show that if you believe that the Big Bang happened at 14 billion years in the past, I forgot to mention, if you can go back, right? It's a good time to actually mention here. If you go back to the age of the universe calculation, which I showed here, if you put k equals 0, if you put r equals 0, if you put m equals 0.3, if you put lambda equals 0.7, if you just do the integrals, just do it, okay, numerically or analytically, and put in the current value of the Hubble's constant, which I have somewhere, it's about 70 kilometers per second per megaparsec. Just do the units right and all that kind of thing. You will see that the age of the universe, which comes out from here, is about 13.7. It's a pretty straightforward exercise. Okay, so coming back here, right? So you can actually show that 13.7, let's say 14 billion years is not enough time for our all, 4 pi steradians of solid angle, so all sides to get thermally connected. So light takes time, right, to propagate. So thermal equilibrium between 2 parts of the universe cannot happen earlier than the time it takes from light to go from here to here, right? Because the equilibrium needs a medium, and light is the fastest medium. So it cannot happen faster than the speed of light moving from here to here. And you can show quite rigorously that 14 billion years is not enough time. In fact, 14 billion years is just enough time for the sky to be homogeneous in about a degree, I think, if my memory calculation is right. It should not be like the uniformity of temperature shouldn't extend beyond a few degrees here, a few degrees there, a few degrees there, a few degrees, like patches, right? It shouldn't be this extremely homogeneous isotope. So it's still a mystery. Okay, so that's part of the unknown. Dark matter, I wouldn't go too much, but I'll just give the basic, the most interesting, one of the most interesting, the first for sure. It was one of the first to propose was an eccentric physicist called Fritz Zwicky, and then some of the crucial observations was done by Vera Rubin in 1970s, where she showed, this is not Vera Rubin's picture here, but the pictures that she drew were very similar. So it's very similar. Here you have some kind of galaxy here. The experimental plots here are the velocity of the galaxy rotation curves, is the spiral arm of velocity, just the linear velocity, like as it's moving. But this curve here, this middle curve here, like the one which goes up and comes down, that's the theoretical prediction, for the simple reason, if you equate even Newton's gravity, which is gm over r squared, to the centripetal acceleration, you see the velocity must go as, just cancel the r, right, and take the square root. It must go as 1 over square root of r. So it should decrease with time, with distance. So the velocity of the galaxy rotation curve should decrease with distance from the center, as it must, because as you go from the center, the gravity decreases, the force of gravity decreases, and it's the force of gravity which is making things go around, so it must become slower and slower, right? But remarkably, not that it just does not slow down at this rate. The actual curve is like this. So it does not slow down at all until you can't measure it anymore, right? So there is clearly a discrepancy between what's observed and what's you predict, and this discrepancy would be this line here, right? This vertical distance here. That would be the discrepancy. So clearly things don't match, right? So therefore, there are at least two possibilities. One is that your theory is wrong, so you have to change Einstein's theory of gravity, and that's quite possible. That's a very exciting prospect. The other, perhaps the simpler solution, is that you have a lot of hidden matter in there, which you can't see. So clearly, this is a case for dark matter. Okay. Now, as you can see, it's easy to postulate. However, dark matter must assume a very specific set of configurations for these curves to work out exactly. And that's not easy. That's part of the problem. And you need exactly the right amounts of dark matter. I mean, it doesn't have to agree, right? But with the theoretical curve, which means there's some excess matter, let's just say, but the excess matter needn't have to be exactly that the curve is a horizontal, right? So it could have gone up this way, or it could come down like this, not quite matching with the theoretical curve. But to make it exactly like a horizontal line like this, like straight, constant, dark matter must be very, very specially configured, and that's not always easy to envisage. And the most important thing is none has been found. So there are lots of candidates for dark matter: weakly interacting massive particles, supersymmetric particles, black holes, gravitons, like axions. Like there are as many candidates as the letters in the alphabet. But in the bottom line is, so far none has been found. If you find it tomorrow, then yeah, that's the solution. If you don't find it in several decades, then maybe we have to think of some alternatives. So that's another puzzle which we don't know about. Dark energy, again, I would not go into the details, but you can arrive at Hubble's law, or most of it anyway, from Newton's law of gravity. But you see, Newton's law of gravity does not give the pressure term, which when negative gives rise to accelerated expansion, right? So right-hand side is negative, which means Newton's cosmology, Newtonian version of cosmology, would not give you an accelerating universe. So that is a shortcoming. So you have to invoke Einstein's gravity in some sense, right? And I kind of purposefully found a picture of Newton, which is kind of old and kind of outdated.
Excuse me, sir, your
Yes.
audio. Now.
Okay, thank you. Yeah, I'm almost at the end. So you actually need something more radical than, and that's why I put Einstein in this kind of radical picture. So you needed something new, which is the pressure, and Einstein's gravity does give this pressure term here, which when negative, if it's not there, it cannot be negative, right? It's just not there. If it is there, then it can be positive or negative. Positive for radiation, negative for the cosmological constant. But so it's negative. Pressure with the cosmological is there. It's not just there, 70%, but we don't know what exactly it is. Okay, so these are a lot of unknowns. I'm aware of the time, so maybe I will not go too much in the speculations. I'll go straight to the conclusions, the summary, and let me put another problem. Just state the problem. As I said, the spatial flatness of the universe is a mystery. Why is it spatially flat and not? It could have been the other two cases as well, and the problem of Big Bang singularity, the problem is it could have happened, and there's nothing which says it cannot, and nothing which says it should have, necessarily should have. But the problem is, if the Big Bang singularity had happened, then the scale factor would go to 0, the density would go to infinity, the curvatures go to infinity. If you remember, they're all 1 over a power something. So if a goes to 0, then the densities blow up. And when something is infinite, it's not a very large number. It means that the laws of physics, or the laws that you are talking about at that point of time, they break down, right? And when laws of physics, like Einstein's equation or Friedman equation, as they're called, break down, it is a loss of predictability. And loss of predictability is the same as saying that the laws of physics break down. So we don't want, if it is the way it is, we cannot dictate nature how she will behave. However, we always hope that there is a theory which will remain predictable, maybe a new theory. But if there's Big Bang, then the laws simply break down. And and this is where I'll kind of end. So one way out of this whole conundrum is by assuming quantum mechanics. Remember, all the slides that I have, those G's, the C's, I just set it to 1. There's no H bar. So when you put quantum mechanics, for one simple thing, things get jittery, right? So if you cool down something to even 0 degree Kelvin, there's still a little bit of motion. So quantum mechanics actually may prevent the collapse of the universe in the past to give a Big Bang singularity. Now that's in the realm of speculations, so I'll not go into too much of details. And I'll just summarize that as I tried to argue, that the universe is very simple at large scales. It's homogeneous, isotropic, spatially fat, 3 types of matter, and it follows the laws of general relativity. How much simpler can it get, really? But there are quite a few open questions. There's too much dark matter. There's too much dark energy, like 25% and 70% respectively. The homogeneity, isotropy, and flatness is a problem which we have not been able to resolve, and the initial singularity as well. Now, we need more research. We need, younger minds such as yourself to come up with new ideas and new ways of resolving. I hope we'll be able to see resolutions of most of the problems within my lifetime. So thank you again for your attention, for your kind attention. I'll stop here, and if there are any questions, I'll be more than happy to answer to the best of my ability. Thank you.
Thank you, sir. Do we have time to? So, do we have time for questions, sir?
Yeah, I have time. I have time, but it's up to you guys. So yeah.
Good morning, sir.
Oh,
Okay, so we have a question from one of our alumni who is watching from the live stream. So I will quote him directly here. So while studying cosmology, I read that dark energy could be the cosmological constant, and that there are other theories with a scalar field deriving that expansion. Could you please explain it?
yeah. So that's why. Yeah, good question. Thank you. So there's a subtle difference between dark energy and cosmological constant. I said that there is, but I'm not elaborating on right now. So cosmological constant, again, just like the Hubble constant is not really constant. The cosmological constant also, it's kind of constant, but it doesn't have to be completely constant. It can be like a constant part plus some small dynamical evolution. And when you have this dynamical evolution, you often call it dark energy. So it's like an evolving cosmological constant, whatever it means, right? It just means it's not a constant. Now, if it's not a constant, then you have to model it with some field, right? Anything in the universe which is not a constant is like a field, right? Like the electromagnetic field or the Yang-Mills field. So the simplest way to model a cosmological constant, which is homogeneous and isotropic, is a scalar field, because a scalar field doesn't have any direction, right? A vector field would have a direction, right? So scalar field is the simplest way to model a dynamical cosmological constant. If there's a scalar field, there can be, well, there's of course a scalar kinetic term, surely, but there can also be a scalar potential term. So essentially that's the way, and then you can play around, you can do a lot of, try to do a lot of predictions from that model and try to check with observations. But that's essentially what it is.
Okay, sir. We also have a follow-up question from him. So I will quote him. Also, when radiation gets redshifted due to expansion, what happens to the lost energy due to change in wavelength?
Right. So energy momentum is still conserved. It may appear that it's lost, but it's not lost, because for the simple reason that the energy momentum conservation law is ingrained in Einstein equations. So if you would like to, technically, Einstein equation is what it is, like R mu, etc. is T mu. If you take the covariant derivative of both sides, it's zero. It's identically zero. And that's a statement of the conservation of energy. So it seems that energy is not conserved. I can try to give more visual picture. We may or may be useful. It's like, yeah, it expands, but now it's in more space. So the energy remains fixed. But mathematically, you can show that energy momentum, like the conservation, is never violated. It may look apparently because it's expanding and all, but it's actually not. So.
Okay, so now I have my own question. So what I wanted to ask is, all of the while we have been assuming that universe is isotropic and homogeneous. What if we instead assume that it's not ideally isotropic and homogeneous, but it deviates from all of these qualities? So what effect will it have on the global curvature of the universe and its evolution and the nature of universe, whether it will be infinite or it will be multiply connected and all such properties?
Yeah, so it's a good question. So I'll answer to the extent that I remember. So firstly, again, you can look at it from theoretical experimental side. From the theoretical side, there are lots of viable models in the universe which are not homogeneous and isotropic. What are the total number? Like if it's homogeneous isotropic, it's in the 3, right? Like flat,
Yes, sir.
sphere, saddle. If it's not, then I don't remember the number. It's still finite. I think the possibilities, but exactly how many, I have to look it up. remind myself, but it's well understood and well studied. So it's a well understood thing because even like 50 years ago, people were sure that it's homogeneous and isotropic. So it made sense to. So in the theoretical side, it's pretty on solid ground. On the experimental side, it's possible, but remember that, and it's quite possible, right? That it's not homogeneous and isotropic at the fundamental level, but that violation or the deviation from homogeneity and isotropy can't be large. It cannot be large, right? Because it's observed to be exact in 1 part in 10 power 5. So on the theoretical side, you have already the models in place which can handle, right? On the experimental side, you need more like better and better observations. And if it's beyond established observationally beyond reasonable doubt that there is indeed a small but inhomogeneity in anisotropy, which is intrinsic, not due to perturbations, is intrinsic in the space-time structure of the universe, you have to deal with it. Like you have to put it in a proper theoretical model and try to explain. So
Okay, so I mean, can you give some examples? What will be the nature of universe, like infinite or the connectedness or topological properties of the universe?
yeah, it depends on the model really. So I think all of the above is possible. Again, I have to look up the details, but there are lots of models with lots of things. So topologically non-connected or disjoint, it's a little bit more complicated, but I suppose it might be possible, right? So
Yeah. Okay, sir. Thank you, sir.
thank you.
Thank you, sir. Is it possible for you to share the slides and maybe suggest some resources to start
Sure.
read it?
Sure. Can I like later today, can I email them?
Sure, sir. Whenever you get the time, please
Okay.
send it.
Okay. I can certainly email them. I'll check the slides themselves might have some references here and there. I will check it. If not, I'll be happy to provide some references to
Sure,
get
sir.
going.
We have one more question, sir.
Sure, of course.
Hello. Could you please, just wondering, so you have assumed that this dark matter and dark energy, they follow the GTR equations. So are there any experimental evidence supporting or against it that they actually follow GTR, or is there some plans to make those experiments in the
Yeah,
near future?
so that's again that's also it's a very good question. So observations are observations, right? That doesn't
Hmm.
depend on models. So homogeneity, isotropy, that's we see. We cannot challenge it to the extent accuracy 1 in 10 power 5. So that's going to set in stone. Now we have to put it in a theory, and it's an assumption that general relativity is correct. It's an assumption. Why? Because that's a very good question. Because general relativity, gravity directly has been verified only from about a tenth of a millimeter, like direct verification, to the planetary scale, like perihelion precession of Mercury or that kind of thing, right? Beyond planetary, if you go to galactic scales, you can still assume GR to be valid, but you have to put in dark matter. It's not valid otherwise. You have to ad hoc put in dark matter. Like look at lensing thing and things like that. It doesn't work without dark matter. So you can still say it's good, but provided you assume dark matter. At the cosmological scale, it gets even more interesting. You can still assume GR is valid, but you have to put in dark energy or cosmological constant. It's only then that GR becomes valid, right? And then you can say, well, that's good. So you have dark matter, it's valid. You have dark matter energy, it's valid. It's all good. It's all valid, right? I could say that. But there's a problem with that because none of the two have been observed,
Yeah.
right? Right? So if dark matter was observed, GR would still be valid. There's no question about it. And same for dark energy. But neither of them have been observed directly. So therefore, there's always the possibility that there is no dark matter, there's no dark energy. But then how do you explain the observations? The only way to explain the observation is if GR is incorrect. I mean, incorrect in the sense incomplete. There's something. So absolutely. So maybe you're quite familiar with it already, but whatever. Like that, theories like FR theories of gravity or modified theories of gravity, and lots of modifications of Bryan-Sticky theories of gravity, scalar tensor theories of gravity. So there are lots of modifications of Einstein's gravity or general relativity which have been proposed, which try to explain dark matter, dark energy without, let's say, without dark matter, dark energy, or less amounts of them, there are varied degrees of success. See, now the thing is, now things become messy because you have a new theory, you have to calculate all the observations, estimates, and then so there's no definitive answer, I think. But I personally think it's a definite possibility that GR must be modified, would have to be modified. We don't know.
So is there any plan for any experiment in near future, or is it technically feasible at all?
Yeah, well, to the extent that I know, I'm a theorist, so I keep track of experiments, but from the outside, right? But I think, yeah, so all future cosmological experiment and gravity wave experiments will test these. I think so. So there's quite a bit of even theoretical work already. And if you're interested, you can get in touch with me. I can send some reference and things like that. There's quite a bit of theoretical work on gravity wave detection if the theory of cosmology was different from GR. Right? For example, some of them predict different speed of light and gravity waves. Some of them predict, right? That's remarkable because now you have multi-messenger astronomy, right? You can look at a gamma ray burst. It has been looked at, I think, a couple of years ago. A gamma ray burst whose light and gravity waves are detected simultaneously, right? But what if you see that not exactly simultaneous? Like there's a split second, millisecond difference between the two. That would mean the speeds is different. That would certainly mean that GR is not incomplete because GR predicts the speed of gravity to be the speed of light. So yeah, and that would be, to me personally, that it's just a personal opinion, that is in fact to me a more or an equally exciting possibility as dark matter, dark energy, and we should not keep our minds closed. Just I think that way. So, thanks for your question.
Very nice talk. Thank you.
Thank you. Thank you.
So we have more questions.
Of course. Yeah, I have time. It's morning here, so I'm more worried about there. So.
So in the introduction of the Hubble constant, you introduced a quantity which is the scaling factor called A,
Yes.
which is related to some quantity called omega as the exponential part of the equation of it. Then in the starting of the universe, when the Big Bang happened, the universe was dominated by radiation.
Most of
when,
it, yeah. Radiation was, yes, a lot is an important part.
And in the intermediate part, when the matter condensed and formed like galaxies and stars, then the matter is dominant universe.
I think, yeah.
What is that dominant quantity when the universe expands to infinity? I mean, in the later part of
That's
the
the
universe.
cosmological constant. Because if you look at again, if you have more detail, you can get back to me. I can send you the calculation stuff or references. But if you look at how the scale factor or how the densities evolve, okay? So all densities which are not dark matter or not cosmological constant, but matter, relativistic, non-relativistic, whatever, right? All of them, the densities dilute as the universe expands, as it should, right? So if I have a glass of something and it's a gas, a cylinder of gas, if the cylinder expands, the density decreases. As simple as that, right? So the densities decrease, except the cosmological constant, and just by virtue of its equations and motion, things like that, well, it's a constant. So the cosmological constant remains a constant. So it's like f of x, a function of x, is decreasing, and then f of x is a constant. Even if the constant is really small, at some point it will overtake the f of x, the decreasing function, right? So therefore, in the far future, even if you had a little bit cosmological constant, it will dominate, and that's kind of what is happening now. Okay, I did mention another problem with the cosmological constant. Since you asked, it's a little bit side thing. But cosmological constant, the best estimates, theoretical estimates, don't agree with the value. And the value of the cosmological constant is really tiny, okay? But even though it's tiny, it gives rise to this 70% proportional density. That's one thing. But it doesn't matter if it's tiny. Something which is a constant, so 1, will dominate 1 over x for some x, or 1 over x squared, right? So in the end, it's the cosmological constant which rules if nothing else happens, quantum or something, and the universe will kind of explode exponentially. Thank you.
Thank you, sir. We have one more question.
Of course.
Hello, sir.
Hi.
So my question is, redshift happens due to three reasons actually: the Doppler effect, the gravitational redshift, and the cosmological expansion. So how are you able to predict the age of the universe using just one source, like using just the cosmological expansion.
Right. So that's where the details coming. So if you look at the Einstein equation, the Friedmann equation, as it's called, and if you remember the theoretical, where you have the integral from 0 to infinity dz divided by something square root, you had all this. It's just the way the equations work. Basically, because Einstein equation relates geometry to matter, right? So the geometry is dependent on the matter, and the geometry in the end determines the redshift. And all the three quantities that you said, like the velocity redshift, the curvature redshift, and the expansion redshift, they're all taken into account together in Einstein's theory of gravity, right? You don't have to separate them. I mean, you can, but
So are
they're
they
all.
so are they
Yeah,
related? Yeah, are they independent? Like,
it depends on. It follows, like you can't really separate all the three. It's one big thing in the Einstein equation, because you can say that one is due to velocity, you can make this linearization and things like that, but the Einstein equation as a whole gives rise the full kit of Doppler shift, which has all the ingredients in it. So I
thanks,
just
sir.
said that. Yeah.
Hello, sir. Actually, my question is on baryonic asymmetry, basically. Initially, you said like early universe was dominant with radiation. So, what may be the possible reasons for this asymmetry in matter and antimatter? Matter, basically.
Yeah, really good questions. Yeah, I don't think anybody knows. So what is the right? Because you have a huge asymmetry, right? There's no antibaryons, hardly any. You could create them in the lab. And there are, I don't know if you're aware, but if not, you can look it up. There are three conditions called the Sakharov conditions. So, and I have to look up all the details. But there's three conditions called Sakharov conditions. I think at least, I hope what I'm saying is not wrong. At least one of them needs to be violated for the asymmetry to take place. So any theory which predicts an asymmetry in baryon and antibaryon has to satisfy, has to be in accordance with the Sakharov conditions. That's not saying much. That's just saying that we understand the problem a little bit better, but I don't think anybody really understands why exactly. Yeah, that's something, you young guys can probably solve the problem.
Is there a chance in which like these like matter part and antimatter part are very much far apart, and also they are indistinguishable with radiation? So is there something like is there a chance of something like that?
It is, but antimatter, remember, depends on what you mean by antibaryons. I assume that like kind of baryons, but with the opposite charge, right? But then it's possible. I mean, you have to do, devil is in the details, that they say, right? So you have to propose the theory, you have to work out the details. Often what happens when you propose a new theory, and I'm not trying to be discouraging in any way, you have to propose hundreds and thousands of theories, because only one or two will turn out to be right. Most of them will turn out wrong, and that's holds for everyone. So but just kind of, when you propose something new, often what happens that you get what you want, but you also get things which you don't want. Okay, so there's a lot of unintended consequences, unintended predictions, and you have to get rid of them, and that's often a problem. So yeah, I mean, if you or somebody else has a specific theory, and if it makes specific predictions which match the observations, then yeah, it could be a serious theory. So
Thank you, sir.
thank you.
Thank you, sir, for taking time out from your schedule to interact with us. We hope we can host you again and learn more from you sometime in the future.
Thank you.
Thank you.
It was my great pleasure. So I wish all of you the best in your work, your physics future. Stay curious, ask a lot of critical questions, and all the best to everyone there. So thank you for your invitation. Thank you. Okay, take care. Bye.